Okay, I'm going to get started. Over the last few classes, we've introduced electric field, electric flux, electric potential. These are all the theoretical ingredients in understanding how electric forces between electrical charges work. So you know all the ways that we think of how electrical forces between electrical charges work. From today's class, over the next few classes, up to test 1, we're going to talk about applications of electrical forces between electrical charges to electrical circuits. We're going to introduce components of electrical circuits, capacitors is this class. In future classes, we'll talk about batteries, we'll talk about resistors, and we'll build up electrical circuits. So that's basically the plan. On the screen are the topics I want to cover today on capacitors and capacitance. So I want to introduce capacitors, and in particular we'll talk about a parallel plate capacitor. I want to talk about capacitors in parallel and capacitors in series. I want to talk about capacitors and energy, and this one should have been at the top. I want to talk about the meaning of capacitors. That should have gone first. Don't know what happened there. Fell off the top to the bottom, like Humpty Dumpty. Okay. Gosh. So let's start with what are capacitors? What is a capacitor? So capacitors are electrical circuit components, and they're electrical circuit components that typically we use when we send or receive data. That's an important use of capacitors. And also when we detect movement or motion, that's another important use of capacitors. So, you know, I don't know how much time I spend on my phone. I'm not on it when I'm sleeping, but most of the rest of the time I seem to be on it. When I'm using my phone, what am I doing? I'm sending and receiving data. That's one thing I do on the phone. Well, that's an example of capacitors. And when I'm swiping left or right or whatever, it's detecting my movement. That's the other use of capacitors. So phones are a classic example of uses of capacitors. When you're sending, receiving data, that involves capacitors and capacitance. When you're swiping left and right, that involves capacitors and capacitances. Okay. From the physics perspective, capacitors are circuit components that they store charge, electrical charge, and they store energy, electrical energy. So we'll be talking a lot about the charge storage, energy storage of capacitors. From the physics perspective, a capacitor has a capacitance that reflects how able or unable it is to store charge and store energy. So capacitance characterizes each particular capacitor. It's a number, it's a value that characterizes a capacitor's ability to store charge and energy. It's given the symbol C and it's measured in farads, and we'll talk about that later on. This picture kind of describes a capacitor, tells us what a capacitor does. And actually the next slide also further describes a capacitor and what a capacitor does. So key things about a capacitor, I've listed them as these bullets here. A capacitor consists of two conductors, a pair of conductors. So we're always going to have two conductors in our capacitors. Charge is placed on those two conductors. We often call those two conductors two plates on which we put the lunch, which is the charge. So we've got two two plates, two conducting plates, and we put charge on those two conducting plates. And we always put equal amounts of equal and opposite charge on those two plates. So we'll put positive charge on one plate, equal amount of negative charge on the other plate. Really, we just move some, say, electrons from one plate, making it positive, to the other plate, making it equally negative. So that's how we use a capacitor. By doing so, when you charge up one plate conductor positive, the other plate conductor negative, you're creating an electrical potential difference between the plates, and you're creating an electrical field between the plates. And so that's what we're accomplishing by charging up the two plates with equal and opposite charges. We're accomplishing a landscape of electrical fields and electrical potentials. And I'm showing that on this sketch here. So on the sketch, here's one of the conductors upstairs here. Here's the other one of the conductors downstairs here. On the downstairs conductor, I place some positive charge. On the upstairs conductor, I place a negative charge. Remember that within the conductor, the field is zero, the charge is on the surface of the conductor, and the potential is constant. So this is like a plateau of constant potential and zero field. And also on negatively charged conductor, that will also be a plateau of constant electrical potential and zero field, with the charge actually residing on the surface of the conductor. Between the conductors then is this wonderful electrical landscape of electrical field lines, electrical potential, contours of equipotential. And I've tried to picture that here. Look at the field lines. They're pouring out of the positively charged conductor, and they're entering in, ending up on the negatively charged conductor. And they're a landscape here. There's also the landscape of electrical potentials, of constant electrical potentials or equipotentials. I pictured those with the dash lines here. So everywhere on this dash line is constant electrical potential. Everywhere on this dash line, everywhere on this dash line, constant electrical potentials. And of course, maybe most importantly, the potentials on the two conductors. This is a constant and this is a constant too. That's the electrical world. That's the electrical landscape. Okay, this is a little bit more information, a little bit more detail on how the capacitor works. So I said we use a capacitor by charging up the plates of the capacitor with equal and opposite amounts of charge. Let's imagine that we gradually charge up the plates of the capacitor, gradually increasing the amounts of positive and negative charge on the two plates. If you gradually charge up the capacitor, then you gradually increase the potential difference between the plates of the capacitor, the voltage difference between the plates of the capacitor. So as I gradually add charge to the two plates, I'm going to gradually grow the potential difference between the two plates. And that's what the graph is showing. The graph here is showing horizontally. This is me adding charge to the plates of the capacitor. Remember, I'm adding positive and negative charge to the two plates, but I'm just imagining the amount of charge I'm adding. And then vertically is the corresponding voltage between the two plates of the capacitor, the voltage difference between the two plates of the capacitor. And then the blue line here is telling us how the voltage between the plates varies with the charge on the plates. If we've only got a little bit of charge on the plates, the voltage is small. If we've got a lot of charge on the plates, the voltage is large. This graph is showing us that the voltage between the plates is actually just proportional to the charge that we've placed on the plates. Here's an equation, or actually here's a pair of equations, that explicitly describe that idea, that the charge on the plates of the capacitor and the voltage between the plates of the capacitor are going to be proportional to one another. And further, they introduce this quantity I mentioned, the capacitance of the capacitor. So if you look at the top line, it simply says that the charge on the capacitor's plates, here's an example, and the voltage between the capacitor's plates, here's an example of the voltage difference. Those two quantities are proportional to one another. If you increase the charge, you'll increase the potential. Reduce the charge, you'll reduce the potential. The proportionality constant between the charge and the voltage is the capacitance. It's the capacitance of the capacitor that is different for different capacitors. And so that's the quantity C here. It plays this role of a proportionality constant in the relationship between the amount of charge and the amount of potential on the plates or between the plates. On the graph, this capacitance is actually 1 over the slope of this line here. What I mean by that is, if this line was steep, if the voltage grew quickly as you added charge, then that would be a small capacitance. It's sort of reflecting that capacitor has a small capability of storing charge, because when you add charge, the voltage grows quickly. On the other hand, this shallow line here with a small slope, this actually corresponds to a large capacitance. This is a capacitor you can add a lot of charge to the plates of the capacitor, and the voltage doesn't grow very quickly. So this dashed line here, the steep one, is small capacitance. Voltage is growing quickly as you add the charge. This shallow line here is a large capacitor with large capacitance, where the voltage grows slowly as you add charge. The steep one, hard to store charge on that capacitor. The shallow one, it's easier to store charge on that capacitor. Here's just an example of using that relation between charge on the plates, voltage between the plates, and the capacitance of the capacitor, C. This is kind of like the master equation for the capacitor. We'll meet later on master equations for batteries, master equations for resistors. And this is the master equation that tells us the relationship between the different electrical properties of the capacitor and its individual capacitance. So from the last slide, I rearranged the equation in the last slide, which was about the fact that the voltage on the capacitor grew with the charge on the plates of the capacitor. It introduced the coefficient of proportionality, the capacitance. I've rewritten it as an equation for the capacitance. It's simply the charge on the plates divided by the voltage between the plates. So you can figure out the capacitance of a capacitor. If I put some charge on the plates, then I measure the voltage. If I divide the charge by the voltage, that will give me the capacitance. Or I could be doing it the other way around. I could apply some voltage across the plates for the battery, and then measure the charge that appeared on the plates. Then again, I just divide the charge by the voltage, and that will give me the capacitance. So this is straightforward to calculate the capacitance from the voltages and the charges that you measure. And that's all I've done here. In this little example, I happen to put, I've got a car battery here, put 12 volts across the plates of the capacitor. I figured out, somehow, I don't know how, that there were 36 nanocoulombs of charge on the two plates, positive on one, negative on the other. All I've got to do is divide that 36 nanocoulombs of charge that's appeared on the plates by the voltage that I applied across the plates, and that's going to give me the capacitance of this capacitor. And you see that we've got 36 times 10 to the minus 9 coulombs. So remember, a coulomb is a huge amount of charge. You'll never have that in an electrical circuit. Amounts of charge in electric circuits are nanocoulombs or picocoulombs. So we've got, with a car battery, we've got 36 nanocoulombs of charge, positive and negative charge on the two plates. We're just dividing it by the voltage supplied by the car battery, and that gives us a capacitance of 3 nano, 3 times 10 to the minus 9 farads. That was the unit of capacitance. I'll just show you a few capacitors before we go on and we go on and talk about a little more the capacitance of a capacitor for a particular type of capacitor called a parallel plate capacitor. So on this overhead here, these are capacitors. Each one of these little units here is a capacitor that might be in some electrical circuit in your home or in your car or in whatever. Let's take a look at a couple of them. Look at this little guy down here. He's pretty tiny. And this is a 0.001 microfarad capacitor. So this is a 1 nanofarad capacitor. So that's a small capacitor, and it's physically small. It's physically small, and it also has a small capability of storing charge because it's got a small capacitance. This is a much bigger capacitor. So this is 0.33 microfarads, or 330 nanofarads, 330 times bigger capacitance, meaning it's got 330 times bigger ability to store charge. It's physically a much bigger capacitor. And not just physically a bigger capacitor, it is more capable of storing charge. So there's just a few examples. Let's talk about a special type of capacitor. It's called a parallel plate capacitor. There are other geometries of capacitors. There's spherical capacitors. The Earth is a spherical capacitor, a really big one. The cells in your body are approximately spherical capacitors, really small ones. We're going to talk about parallel plate capacitors, because parallel plate capacitors have a simple equation, a simple formula for their capacitance. And so that's why we're going to focus on them. Okay, a great example of parallel plate capacitor is thundercloud. The bottom surface of the thundercloud and the upper surface of the ground are like two parallel plates. And that thundercloud forms with the ground a parallel plate capacitor. So that's a natural example of parallel plate capacitor. But we're going to look at some man-made examples of parallel plate capacitors. Here's a picture of a parallel plate capacitor. It's a sketch of a parallel plate capacitor showing the geometry of a parallel plate capacitor. Why do we call it a parallel plate capacitor? Because it's got two parallel plates. So here's the top one, and here's the bottom one in red and blue. We put positive charge here on the top one and negative charge on the bottom one. These are conductors, so that charge spreads out over the surface. It doesn't just reside at some location in the volume. It spreads out all over the surface. And it's the reason for the electrical field in orange, the field lines in orange that run from the positive charges to the negative charges, and the electrical potential. In blue is the lines of contours of electrical potential that run from the constant potential on the upper conductor to a constant potential on the lower conductor. So that's the picture. In the picture, we call the area, this is the cross-sectional area of the plates, we call that A, and we call the separation of the plates, we call that D. And the question is, how does the capacitance of this capacitor depend on the area of the plates and the plate separation? And the special thing about the parallel plate capacitor is we can write down a very straightforward, simple equation for the capacitance in terms of the area of the plates and the separation between the plates. Just one point. This is a cross section of this capacitor. This sketch is a cross section of this capacitor. So you've got to imagine this top plate here is a plate like this. It's coming out of the screen towards you. And then below it is a bottom plate. So these plates are two-dimensionals with some areas and with some separations, with the area A and separation D. Okay, well this equation down here is the capacitance of the parallel plate capacitor. A few comments about it. So the capacitance of the parallel plate capacitor depends on its geometry. Firstly, this equation only applies for this arrangement of a parallel plate capacitor, two parallel plates, so that depends on the geometry. Secondly, the equation for the parallel plate capacitor depends on the components of the geometry, which are the area of the two plates, that's the A in the equation, and the separation between the two plates, that's the D in the equation. So it's an equation that tells you the capacitance in terms of the geometry of our parallel plate capacitor. There's one other quantity that's in the equation. It's the electric permeativity, which, if you remember, is related to the Coulomb constant, which, if you remember, both epsilon naught and K, the Coulomb constant, reflect the intrinsic, the natural strength of electricity. So the fact that this is an electrical arrangement of plates comes in through epsilon naught. Anyway, if you look at this equation, it tells you a couple of important things. The bigger the area of the plates, is the bigger the capacitance. The smaller the separation, it's in the denominator, the smaller the separation, the bigger the capacitance. So supposing you get a job, you're asked to make some capacitors. If you want to make really big capacitors, you've got to make big plates, large A, you've got to have them closely spaced, small separation. That will make a big capacitance that's capable of storing a lot of charge. If you want to make, I really need a picocoulomb, picofarad capacitor. If you want a really tiny capacitor, you've got to make small plates, and you want them well separated. You want to make A small and D big. And so this is kind of the rule book for how you would make a large or a small or whatever capacitor you want, whatever capacitance you want. Let's just look at a quick example involving that, I think. Oh no, I got a quiz first. Yeah. So this is a quiz about parallel plate capacitor. Let me publish it. In this question, we've got three parallel plate capacitors. C1 left, C2 center, C3 right. We're asked to order them, rank them from largest capacitance, largest ability to store charge, to smallest capacitance, lowest ability to store charge. If we look at the pictures, we see that these capacitors, they're parallel plate capacitors, but they have different plate areas. Plate 3, capacitor 3 has the smallest area, and they have different separations. Capacitor 2 has the smallest separation. So just think about it and rank order them from largest capacitance to smallest capacitance. Okay, let's get going again. Three capacitors, three parallel plate capacitors, but with different plate areas and different plate separations. Make a big capacitance, you want a big plate area, and you want a small plate separation. Capacitor number 2 has the best combination of a big area, It's got as big an area of plates of any of the other capacitors, and it's got a small separation. It's got as small a separation of any of the other capacitors. And so capacitor number 2, that has the highest capacitance. Big area to put the charge on, small separation between the charges. So this is a big capacitance. Capacitance number 3 has the smallest capacitance. So it's got this combination of the smallest plate area, which makes for a small capacitance, and a large plate separation. So this capacitor number 3 has the smallest capacitance, and capacitor number 1 is somewhere in between these two. So we go to C2, C1, C3. Is the rank ordering from largest to smallest. Everybody okay with that? No. Let's calculate the capacitance of a parallel plate capacitor and explore the charge in the field of a parallel plate capacitor. Let's solve this problem here. So this is a numerical problem. I got a parallel plate capacitor, and I'm told that I'm applying 3 volts to the parallel plate capacitor. I'm told the geometry of the parallel plate capacitor. I'm told that the geometry is such that it has a plate area that is 2 square centimeters, and it has a plate separation that is 1 millimeter. And from that geometrical information, and being told the voltage on the plates of the capacitor, we've got to calculate the capacitance of the capacitor, the charge that's on the capacitor, and the electrical field between the plates of the capacitor. So a whole load of electrical things about the capacitor and its capacitance. So let's go ahead and do that. I'll put this on the document camera. I can put it on both because there's... So I made a little picture to get myself going. Here's the parallel plate capacitor. So when we draw parallel plate capacitors, we draw horizontal lines here for the plates, and these are the contacts with the plates on which we apply, say, a voltage between the plates. And that's what I did. I applied 3 volts between the 2 plates, where the plates have an area of this unreadable 2 centimeters squared and this separation of 1 millimeter. And I've got to find C, the capacitance charge, Q on the plates, and the electrical field in this region between the plates. So we're going to do those 3 things. Find the capacitance. The capacitance of a parallel plate capacitor is electric permittivity of free space. That's a mouthful, and its value is about 9 times 10 to the minus 12 in SI units, times the area of the plates divided by the separation of the plates. So C equals epsilon naught A over D. All we've got to do is fill in the numbers. I won't fill in the number for epsilon naught because it'd take me too long to write it. But area, let's be careful. The area is 2 centimeters squared. There's 100 centimeters in a meter. There's 10,000 square centimeters in a square meter. So this is 2 times 10 to the minus 4 meters squared. And in the denominator, its separation is 1 millimeter. We've got to put that in meters. So that's 1 times 10 to the minus 3 meters. Plug in all those numbers. The value that I got, I wrote it down somewhere. Hope I can find it. I think it was sort of nano farads. No, it wasn't. It's 1.77 picofarads. A pico, what's a pico? A pico is 10 to the minus 12. So it goes milli, micro, nano, pico, femto. 10 to the minus 12 farads. That was easy. What's the charge on the plates of the capacitor? Charge on the plates of the capacitor is related to the voltage across the plates of the capacitor. And we know the voltage is 3 volts, so we can figure out the capacitance, the charge on the plates, as long as we know the capacitance of the capacitor. Remember the master equation for a capacitor. C equals Q divided by V. So I can turn C equals Q divided by V around by multiplying by V to make an equation for Q. So Q equals CV. C, I now know, 1.77 picofarads. V, I was told, 3 volts. So all I got to do is multiply the 1.77 by 3. So that's 5.31 I wrote down here. And this will be picocoulombs. So we've got 5 picocoulombs, a little over 5 picocoulombs stored on our capacitor, determined by knowing the voltage between the plates of the capacitor and its capacitance, its ability to store charge. What about the electrical field? What's the electrical field between the plates? Now the key thing for a parallel plate capacitor is that, remember, the electrical field will run from the positive plate to the negative plate. So I pictured that here. And it actually streams straight downwards from the positive to the negative plate. It's a nice, uniform, constant electrical field from the positive plate to the negative plate. And we looked at this sort of arrangement of charged plates and the field between them in the last class. Remember that the electrical field is the negative slope of the potential. We can figure out the slope of the potential by taking the difference in potential between the top and bottom plates. That difference in potential, I'm just calling it V here. That's a little bit sloppy of me. It's really delta V, the difference in potential between the two plates. But when we start working with capacitors, we start dropping off the deltas. And so it is a little bit sloppy, but it's a little bit of a tradition. So the potential difference between the top and bottom plates is V. If I divide that by the spatial distance between the top and bottom plates, that's the slope. And if I just want the magnitude of the electrical field, because I don't know whether they put positive or negative charge on the top or the bottom, I just want to know the size of the electrical field, I can just compute the size of the potential divided by the separation, the distance between the plates. And so I've just got to fill in 3 volts, 1 millimeter, 1 times 10 to the minus 3 meters, and divide one by the other. Well, look, that's I can do that in my head almost. That's 3 divided by 10 to the minus 3, so it's 3,000. So it must be 3,000 volts or 3 kilovolts. And so that's the electrical field between the plates. Everybody okay with that? Good. Don't know why I did that. I've talked about thunderclouds. Thunderclouds and the ground are big parallel plate capacitors. They have capacitances that are large. This was a sort of picofarad scale. The capacitance of a thundercloud with the ground is the scale of microfarads of capacitance. It's huge plate size of the thundercloud, but it is a large separation between the bottom of the cloud and the earth. But put them all together, you get microfarads of capacitance. Want to move on to electric circuits, you'll be pleased to know.
Draw the slides up.
Thank you. Yeah. I was just trying to engage my brain then. Thank you for pointing that out. I will need that repeatedly. Last semester, everybody was extremely polite to me last semester, and they allowed me to go on for about 15 minutes in this condition where I thought I was presenting slides, and I wasn't. So that's great. I want to start talking about electric circuits. and we're going to talk about electric circuits a lot over the next handful of classes. I'm going to talk about today electric circuits that contain capacitors. That's going to be the main focus. But just a few general words first. Electrical circuits are just assemblies of electrical components, such as capacitors, we've been talking about, but also batteries and also resistors, which are things you know about. So we're going to put those all together over the next couple of weeks. One thing about electrical circuits that you'll always see in the electrical circuits is you need a source of energy, electrical energy. So all my circuits will have a battery in them or be connected to a power outlet. They need electrical energy for an electrical circuit to electrically operate. And we're going to discuss batteries in the next couple of classes. We'll talk more about batteries. When we have an electrical circuit, we'll make a diagram of the electrical circuit, an electrical circuit diagram which describes the layout of the electrical circuit and allows us to figure out how the electrical circuit works, performs. Here's just a few symbols that we're going to use today. The top one is that symbol for a capacitor. It looks like a parallel plate capacitor because you see the two plates in blue, but in general it represents any capacitor, whether it's parallel plate or spherical or cylindrical capacitor. The symbol below is the symbol for a battery that supplies the energy or the power to the circuit. It looks a bit like the symbol for a capacitor, but if you look at the two plates in green there, one of them is big and one of them is small. One of them is long and one of them is short. The way I remember this is that a battery has a positive and a negative terminal. You know, when you put the batteries in the remote control, you have to put the positive and negative terminals in the right arrangement in the remote control. The positive terminal of the battery is the long green line. The negative terminal is the short green line. The long green line, right, if I had a pair of scissors, I could cut it in half and make a plus sign. The short green line is too short for me to cut in half with a pair of scissors, so I could only make the minus sign. So that's the way to remember it. Out at the bottom, there are a couple of switches. This is how we indicate whether a switch is open and the circuit's not operating, or the switch is closed and the circuit would be on. So this is like your light switch in your house or something like that. Okay, so now that was the warm-up. Let's get on with circuits. We're going to do circuits where we've got more than one capacitor in parallel with each other. What does that mean? Well, I'll tell you. And we've got circuits where we got more than one capacitor in series with one another. And again, what does that mean? Well, I'm going to tell you. So circuits in parallel, capacitors in parallel, first of all. This overhead is showing an example of two capacitors in a parallel circuit. And on the left-hand side is kind of a cartoon of this circuit, and then on the right-hand side is what we would call the circuit diagram of this circuit. But they both represent the same thing. So let's look over here. This is kind of the cartoon kindergarten picture version. And in this circuit, we've got a battery down here. So it's got the positive terminal and the negative terminal. It supplies electrical power and electrical energy. Then we've got two capacitors here. We've got a capacitor with the positive and negative plates upstairs here, and I labeled it C1. And I've got a second capacitor in the middle here, positive and negative plates. I've labeled it C2, so I can discriminate between the two capacitors, C1 and C2. This arrangement is called parallel, a parallel arrangement. The two capacitors, if you think about it, are connected in parallel to the two terminals of the battery. So capacitor number one, its left-hand contact is literally connected by a wire to the positive terminal, and its right-hand contact is literally connected by a wire to the negative terminal of the battery. And the same thing for capacitor 2. its left-hand contact is connected by a wire to that same positive terminal. Its right-hand contact is connected by a wire to that negative terminal. This is what we call parallel. This is what we mean by parallel. This is the definition of parallel in electrical circuits. One way of thinking about it, in a parallel circuit, supposing you were an electron in an electrical circuit, and you were going to go walking around the electrical circuit. In a parallel circuit, if there's components in a parallel circuit, as you go through the electrical circuit, from one terminal of the battery to the other terminal of the battery, you can only walk through one of the parallel components. So supposing I'm an electron, I'm running away from the negative terminal because it's repelling me. And I will run up the wire, and I could either go over here through this arm of the circuit, or I could go upstairs to this arm of the circuit. And so that's parallel. Over here on the right-hand side, this is the circuit diagram of that circuit. So I'm just using the symbol for capacitance for C1, symbol for capacitance C2, and the symbol for the battery here with its positive and negative terminals downstairs here. I've also labeled not just the capacitances, but I've labeled the fact that the battery supplies a potential difference. You know, when you go to Kroger's and you buy batteries, you know, you might be buying a 3-volt battery, or if it's the smoke detector, you would need a 9-volt battery. And so you're buying a potential difference that will buy you a supply of energy to the electrical circuit. So I've labeled this potential difference of our battery down here, and it's also labeled the potentials that appear across the two capacitors. There's a delta V1 and delta V2 for the C1 and the C2. And the big question I'm going to ask is, what is the single capacitance, we're going to call it the equivalent capacitance, that I could replace these two capacitors with, these two in the circuit diagram with? What single capacitance could I replace them with that stores the same amount of charge for the same voltage applied? So that's what we're going to figure out. What is the equivalent capacitance of the two capacitors, C1 and C2? You know, C1 and C2, in general, they're going to be different. So a solution to this problem will take into account that those two capacitors could be different, or maybe the same, but it's going to be a general formula for the equivalent capacitance of the two capacitors in parallel. So this slide here, this is not the solution to the problem of what is the equivalent capacitance. That's, I'm building up the, desire for that, whatever the word is. This is the keys to solving the problem. This is a key understanding in solving the problem. When you have two capacitors in parallel like this, these two capacitors have the same voltage across them. So that's a key thing. They're both connected, as we said, via wires between the positive and negative terminals of the battery. So both capacitor number 1 and capacitor number 1 have the same voltage across them, and it's the same voltage as supplied by the battery. And so that's what this first line says here. So this is a very important statement about how the voltages get shared out. And in this case of parallel capacitors, same voltage is given to both of the capacitors. It's different for the charge. This is an important statement about the charge. Capacitor number 1 stores some charge. Capacitor number 2 stores some charge. And the sum of their charges is the total charge that's stored by this arrangement of the two capacitors. So in general, the charges on the plates of the capacitors are not the same. The smaller capacitor will actually store less charge, and the bigger capacitor will store more charge, because the smaller one, for the same voltage, is less capable of storing charge. The bigger one, for the same voltage, is more capable of storing charge. So They store different amounts of charge, and their total charge is the total charge stored by the entire circuit. So those are two keys, and then I'm going to tell you what the single capacitance is that you could replace these two with, C1 and C2 with, arranged in parallel to store the same total amount of charge for the same applied voltage. So that's the original circuit over here on the left-hand side with the two capacitors, where we see a voltage being applied to the two capacitors, and they're storing amounts of charge that are labeled Q1 and Q2. This is the equivalent circuit where we've replaced the pair of capacitors with just one capacitor. We called it the equivalent capacitor, C subscript equivalent. And it's storing the same total charge as these two capacitors were storing in combination. And the value of its capacitance that accomplishes that is this little guy here. It's just the sum of the two capacitors. So the whole moral of this long story is that if you arrange two capacitors in parallel with one another, where they have the same voltage across them, but share the storing of the total charge, the single equivalent capacitance that's equivalent to that circuit is just a capacitor equal to the sum of the two individual capacitors, so C1 plus C2. And then we can use that rule. We're going to use that rule in understanding electrical circuits involving capacitors, because you often get them in parallel with one another. If you want to, I think the next slide is just a visualization of that. Yeah. So what we just said is if you put capacitors in parallel, you make a bigger capacitor. So one way in an electrical circuit, supposing you've run out of big capacitors, but you need a big capacitor, we'll just start putting the smaller capacitors in parallel one another. You'll make a bigger capacitor more capable of storing charge. So it's a recipe or a rule for how to do that. You can see kind of how it works here. Look, here's Merlin, and he's performing the magic trick of turning these two parallel plate capacitors into a single parallel plate capacitor by pushing the plates together. When he does that, right, when he pushes these two plates together, this is a combination of two capacitors in parallel. Right? And if you push the plates together, you see, what do you make? You make one capacitor that has an area of the plates that's twice as big. The capacitance of a capacitor grows with the area. And so when you can see here in this little cartoon that if you do put two capacitors in parallel with one another, it's equivalent to a single capacitor with a plate area that in this case is twice as large, and so it has a larger capacitance. And so just like C equals C1 plus C2 tells you that if you put the plate capacitors in parallel with one another, you get a larger capacitance. This little cartoon shows you how you get a larger capacitance with two parallel plate capacitors pushed together from a parallel arrangement. The other case of arranging capacitors in a circuit is to put them in series with one another. And so I want to show you a circuit with two capacitors in series and how you figure out, again, the equivalent capacitance of the two capacitors when they're in series with one another. So these will be really the same set of slides of what is series, like what is parallel, what is the keys to understanding a series circuit capacitors, like what is the keys to understanding a parallel circuit of capacitors, what is the equivalent capacitance, and how to visualize it. Okay, so this is a cartoon, this is a circuit diagram for two capacitors in series with one another. So again, we've got C1 and C2 upstairs here in the cartoon connected to a battery, and we've got the circuit diagram for C1 and C2 and the battery over here on the right. This is a series arrangement over here. This is a series arrangement of the two capacitors. In the parallel arrangement, each capacitor was connected across the terminals of the battery. In the series arrangement, the two capacitors are connected together in a chain and then connected across as a chain across the two terminals of the battery. So that's what we mean by series compared to what we mean by parallel. Think of it again in terms of imagining you're an electron going around a circuit. In a parallel circuit, you had to go through one capacitor or the other capacitor. In a series circuit, you can walk around the circuit from the negative terminal to the positive terminal by going through both capacitors. So here I am, I'm an electron, I'm running away from the negative terminal because it's repelling me, I'm running down the wire, I go through C2, then I go through C1 to get back to the positive terminal of the battery. So I go through both components. That's the difference between series and parallel. Same question about this arrangement. And we're going to come up with an interesting result, is what is the single equivalent capacitance that I could replace the pair of capacitors in series with that for the same applied voltage would store the same quantity of charge? What is that equivalent capacitance? So that's the question. And again, we're answering this in a general way. It doesn't matter whether C1 and C2 are the same or different. The keys to the castle. The keys here are again about charge and voltage sharing in the series circuit, like they were about charge and voltage sharing in the parallel circuit. In the series circuit, the keys are that the charge on the plates of C1, the left-hand capacitor, and the charge on the plates of C2, that's the right-hand capacitor, so I label them Q1 and Q2. They're the same as each other, and also they're the same as the total charge that's going to be stored on the equivalent capacitor. So I wrote that down here. The charge on the equivalent capacitor is going to be equal to the charge on the two individual capacitors, and they are the same amounts of charge. If you want to understand why are they storing the same amounts of charge? Why would they store the same amounts of charge? Well, one way of thinking about it is think about this little internal wire here that links C1 and C2. The only way to get positive or negative charges on the right-hand plate of C1 and the left-hand plate of C2, because they're an isolated bit of the circuit, is for electrons to run off of one plate onto the other plate. So it must be because the right-hand plate of C1 and the left-hand plate of C2 and the wire connected them are isolated from the battery, that the charge on those two plates, the right-hand plate of C1 and the left-hand plate of C2, can only have equal and opposite charges. That proves that Q1 and Q2 must be the same. And so there's an amount of charge Q that's the same as Q1 and Q2 that's stored in the circuit, and we want to, for a given voltage, we want to find out what the single capacitance is that would store that same amount of charge if we just had replaced the pair of capacitors with one capacitor. So let me show you the answer to this problem. So here's the original circuit. It has the two capacitors in parallel with one another. I've indicated the charges on the plates and the voltages between the plates. They share the voltage from the battery. So that this voltage here from the battery is, some of it is owned by capacitor number 1 and some of it is owned by capacitor number 2. Delta V1, delta V2 will add up to the total voltage that's provided by the battery, the series circuit. This is the equivalent circuit. We've replaced C1 and C2 by the equivalent capacitance that is going to store the same charge, Q1, Q2, as the original circuit here, for the same applied voltage. What capacitance does that? Well, the equation is down here. This equation says that the inverse, the reciprocal of the equivalent capacitance, is equal to the sum of the the sum of the inverses of the individual capacitances. So 1 over C equivalent is 1 over C1 plus 1 over C2. So that's the rule for capacitors in series with one another. Now, when you had them in parallel, when you had capacitors in parallel, you made a bigger capacitance when you put them in parallel. You could store more charge. The reverse is true of this equation. This equation leads to the fact that if you put capacitors in series with one another, the equivalent capacitor is going to be smaller than any of the individual capacitances. So, like we said, if you're building electrical circuits and you run out of big capacitors, you can make a big capacitor by putting the capacitors you've got in parallel. If you're making an electrical circuit and you run out small capacitors, you can make a small capacitor by putting your bigger capacitors in series with one another. Okay, here's just a way of visualizing why you get a smaller capacitance when you put together two capacitors in series with one another. Here's Merlin again, and he's going to perform his magic trick and push these two series capacitors together. So he's going to push them closer and closer and closer and closer until the middle plates vanish into each other. That's what he's done here. What's he left with? He's left with another single parallel plate capacitor, replacing the two original parallel plate capacitors that were in series with one another. But this parallel plate capacitor has twice the separation. Twice the separation means you've got a smaller capacitance. You've got half the capacitance. So we put two capacitors in series, and we've made a smaller capacitor, smaller than either of the individual capacitances. So this is just a cartoon of how that works. Okay, let's get onto some examples. Here's what at first sight might be a horrific circuit diagram involving 4 capacitors in a battery. And we're going to attempt to calculate the equivalent capacitance of this entire arrangement. That's one thing that we're going to try and do. We're also going to try and figure out the voltages and the charges across all of the individual capacitors. So this is analyzing the electrical circuit involving capacitors and batteries. This is what we're going to do now. And it does look like a challenging problem because of the complexity of the circuit, and that I've just given you some very basic rules for how to deal with capacitors in series and how to deal with capacitors in parallel. But we're just going to take those rules and also the equation for a master equation for a capacitor relating the charge, the voltage, and the capacitance, and solve this problem. So first thing I'm going to do is find the equivalent capacitance. So I'm going to find the equivalent capacitance by looking at the circuit diagram and figuring out pieces of the circuit diagram that are either in series or a parallel, where we can apply the rules of series and parallel capacitors. That's the way that you would analyze a circuit diagram involving a complex network of capacitors. And so the first thing I realized is it does look like a very complicated circuit. You know, I got 2 capacitors upstairs here. I got 2 capacitors downstairs here. I got the battery over here on the left. I've got this complicated arrangement of wires. But if I stare at that arrangement for a while, I started to recognize something. These 2 capacitors upstairs here, labeled C1 and C2, are just in parallel with one another. These capacitors downstairs here, C3 and C4, they're just in parallel with one another. I can use my simple rules for capacitors in parallel and replace C1 and C2 by a single equivalent capacitance. And I can replace C3 and C4 by a single equivalent capacitance. And so that's all I'm going to do in my first step. I'm not going to solve the whole circuit in one go. I'm just going to solve a small part of the circuit. The equivalent capacitance of C1 and C2, because they're in parallel, is just the sum of the capacitances. So one's a microfarad, Another one's a 5 microfarad. So the equivalent capacitance is 6 microfarads. I wrote it down here. The equivalent capacitance of these two capacitors down here is just the sum of the capacitances again, because they're in parallel. So I've got 8 microfarads and 4 microfarads. This is 12 microfarads total. So I did that. Now the circuit is starting to look simpler. I just redrew the circuit. This is why I'm not attempting it on the document cancel. It'd be impossible. I'd be redrawing all these circuits. I labeled C1, 2. It's the equivalent capacitance of C1 and C2. Remember, it's the sum of the two capacitors, 6 microfarads. Here's the equivalent capacitance C3, 4. It's the sum of the capacitances C3 and C4. That was 12 microfarads. So I've just drawn these two equivalent capacitances here that store the same amount of charge for the same voltages applied to them. These are now two capacitors just in series with one another. Oh, magic. I can use my other rule. This is if I planned this. I can use my other rule for capacitors in series now. The single equivalent capacitance of these two capacitors in series, well, its reciprocal or inverse is the sum of the reciprocals or inverses of these two individual capacitors. So 1 over C equivalent is equal to 1 over 6 plus 1 over 12. And if you calculate that, 1 over 6 plus 1 over 12, we'd have to make a common denominator, wouldn't we? I've forgotten how to do that, but it will be 2 over 12 plus 1 over 12, which would be 3 over 12. But we want the inverse of 3 over 12 for the equivalent capacitance. So it would be 12 over 3 microfarads. 12 over 3 microfarads is 4 microfarads. And so that's the single equivalent capacitance for the whole circuit. So we solved it. It looked horrendous, looked horrible, but we were able to solve it with our rules for capacitors in series and parallel. What's the voltage across each capacitor? I'm going back to the original circuit now, and I'm going to ask the question of what voltage is across each of these 4 individual capacitors. And actually, if I calculate the voltage across the 4 individual capacitors, I can also figure out the charge that's stored by the 4 individual capacitors. So I can figure out everything about the circuit. But let's just think about the voltages. How on earth am I going to solve the problem of what is the voltage across these 4 capacitors? Again, the trick is to break the circuit down into equivalent components where you can more simply understand how the voltage gets shared. What I'm going to do is do that same first step I did by combining capacitors 1 and 2 and 3 and 4. I'm going to do it again, but I'm going to do it to try and understand what the voltage is across the pair of capacitors in the top half of the circuit and the pair of the capacitors in the bottom half of the circuit. There's an important point here. Remember C1 and C2 in the top row? They're in parallel, so they have the same voltage across them as the equivalent capacitance C12 has. And so this capacitor C12 has a voltage across it that I want to find, but it's the same as the voltage across the capacitors C1 and C2. So if I can just find V12, I've found the voltage across the top pair of capacitors. Same idea for the bottom pair of capacitors, right? They have the same voltage across them as each other and the same voltage across them as the equivalent capacitor, that's C34. If I can just find that, I can solve the problem. So I've reduced the problem to finding these two voltages now. That's a big step, because I can write down a couple of equations that allow me to find those two voltages. The sum of the voltage across C12 and the voltage across C34, because they're in series with one another, the sum of those two voltages must be the voltage supplied by the battery. So I know the sum of V12 and V34 is 24 volts. So this is one equation that I know for these these two capacitors, equivalent capacitors. And this is just the idea that this voltage, 24 volts, is shared between the two capacitors. That's the basic idea here. The other basic idea is that these two capacitors, because they're in series, they have the same charge on their plate. So that's a key idea. Remember, we said they have to have the same charge in their plate because of this interior wire here. The bottom plate of the top capacitor and the top plate of the bottom capacitor are connected to one another, but they're isolated from the circuit. So you can only equally and oppositely charge these two plates. So the two capacitors in series have the same charge on their plates. So I started with that idea. Q12 equals Q34. This charge upstairs stored here, and this charge downstairs stored here must be equal. I replace the charges in terms of the voltages across those capacitors. This is the master equation for the capacitance. C equals Q over V. That's all I use there. And I plugged in the values of the capacitance. Really, I just plugged in the fact that the lower capacitance is twice as big as the upper capacitance. And we find out that V12 is twice as big as V34, just because the capacitance of V34 is twice as big as the capacitance of C12. Let's take a breather. But what I've just done, based on two basic principles, the voltage sharing across the capacitors and the fact that they have the same charge on the plates of the capacitors because they were series capacitors, I just ran with those two ideas and I've generated two equations for the two unknown voltages. The sum of them is 24 volts. So whatever V1 and 2 is and V34 is, the sum is 12 volts. But also, from understanding the charges on the plates, we learned that V12 must be twice as big as V34. If you're a mathematician, right, you recognize there's two equations, two unknowns. So you can obviously solve these two equations, two unknowns. But if you've just got common sense, right, you can also solve it. V12 is twice as big as V34. What two numbers, where one is twice as big as the other, could add up to 24? Well, I've got the answer. 8 and 16. Okay, 16 is twice as big as 8, and 16 plus 8 adds up to 24. So the solution to this problem here is that V12, which is the bigger voltage, this is 16 volts across here, and V34, that's the smaller voltage, is 8 volts across here. So this one's twice as big, this one's half as big. The sum of them is 24 volts. And so that's what the two equations demand. So at that point, you've got the voltage across all four capacitors, because C1 and C2 also have this 16 volts across them, and C3 and C4 also have this 8 volts across them. We've solved the whole circuit. I won't solve, on the next slide, there's the charges on the plates, but that's easy to find now, the charges on the four plates, because you know the voltage across the four plates of the four capacitors, you know the capacitances of the capacitors. You can just use C equals Q over V to find the charges. I won't solve it because I want to turn to one last thing. Storing energy in capacitors. So here's a cartoon of storing the energy in the capacitor. Battery is going to supply the energy. Capacitor is going to store the energy. Switch is going to make the circuit. When you close the switch of this circuit, which is just a circuit involving one battery and one capacitor, what happens? What happens from an energy perspective, a power perspective? What happens from an energy power perspective is that the chemical energy in the battery, so batteries are, when you go to Kroger's and you buy your batteries, 9 volts, 3 volts, whatever, you're buying a little reservoir of chemical energy. And when you connect it in a circuit, is going to get turned into electrical energy, driving the electrons around the circuit. So when we close the switch, the chemical energy in the battery is going to go down as it supplies electrical energy to the circuit, which actually gets stored up in the capacitor. When we close the switch, we store charge on the plates of the capacitor. It creates electrical field, electrical potential between the plates of the capacitor. That all stores electrical energy in the plates of the capacitor. So you can look at circuits in different ways. You can look at circuits from the motion of the electrons around the circuits and the forces they feel. You can look at circuits from the perspective of energy, and that, different circuit components, like a battery supplies energy, a capacitor stores energy, resistors, you will discover, dissipate, what we call dissipate energy. So it's another way of thinking about circuits. There's also another way, we won't talk about it much, but you can think of circuits as arrangements of supplying and distributed information around the circuit. But we're going to focus on the forces and the energy perspectives. Anyway, this is the energy perspective, and I want to give you an equation for the energy that gets stored in the capacitor. And that's this slide. So the energy that's stored in the capacitor, we call it its electrical energy, its electrical potential energy. So here's the symbol we're going to give it, and I think this is what they use in the textbook. Potential energy with a subscript E for electrical. You can write, it's one equation, but you can write it in three different ways involving capacitance, charge, and voltage. If you just want to write it in terms of the charge on the plates of a capacitor and its capacitance, it's this equation here. It's half Q squared over C. If you want to write it just in terms of the voltage between the plates of the capacitor and the capacitance, it's 1/2 times the capacitance times the voltage squared. Or you can write it without referring to the capacitance as just 1/2 times the product of the charge and the voltage between the plates. So those three ways of writing it, they're all connected to one another. Sometimes one's more convenient, sometimes another one's more convenient. They're all just related by that master equation for capacitors, C equals Q over V. The equation tells you that if you put a lot of charge on a capacitor, then that's going to it tells you that, let me say it again, that if you have a large capacitance, so if C was large, you can easily store the charge. There's a small energy cost for storing charge. But if C is small, then there's a much bigger energy cost for storing charge. So storing charge and energy on a capacitor is always this sort of balance between how much energy you have to use to store how much charge. Big capacitors can store a lot of charge for a little amount of energy, and small capacitors only store a smaller amount of charge and cost a lot of energy. I want to end up with a demonstration that capacitors store energy. I'm going to put this on the overhead camera. I got an arrangement of 3 identical capacitors. There's 3 over here, there's 3 here. These are connected in parallel. You can probably see they're in parallel because all the terminals upstairs are connected together. All the ones downstairs are connected together. These are connected in series. I'm going to charge up these. They're in parallel, so they have a big capacitor. So they store a lot of charge, will release a lot of energy. These are in series. It's a small capacitor. So they store not much charge and not much energy. Okay. I'm going to I'm applying a volt. Oh no. I mustn't do this the wrong way round. I'm going to close the circuit on the parallel arrangement. I'm going to charge up the parallel arrangement. I've got to wait a few seconds. I've got to wait a few seconds for these capacitors to charge up. I'm charging up the ones over here, the parallel arrangement. It's going to store a lot of energy. I'm going to then let that charge just sit on the plates. and then I'm going to short out the plate. So basically with this, which has got an insulating arm to it, I'm going to connect together the two terminals, and we'll suddenly, in a moment, release the charge on the plate. We're going to release the charge, and we're going to release the energy.